Yeah, what else? We can see that it's not stripped, so that's good, meaning we have debug symbols to play with. Let me just put this to be a bit smaller, actually. Okay. What did I do? All right. Okay, so I just like to have my notes. So we have this. Okay, the next thing I do is I do check sec. This just gives me like a sanity check to know like what I'm dealing with. In this case, there's a canary, there's an X bit, and there is PIE. So let me first copy this and then maybe go through. All right. I made a really cool diagram recently. Let me just open it and then maybe explain before we continue. Will I find it? Was it this? Nope. I can't find it. I can just go here. Okay, yeah, I can't find it, but it's fine. So I made a diagram just to explain the canary. You guys can see, right?
Yeah.
Okay, sawa. So this was for another CTF challenge, but the idea is the same. So just a visualization of how the stack looks like and where the binary sits. I mean the canary sits. So we all know, I hope, that the stack grows upwards from down here going up. So when you load a function stack into so think of it as like a Russian doll. I hope you guys know what a Russian doll is. It's like this is a Russian doll. So like you open the big one, inside there's a small one, inside there's a small one, there's a small one, there's a small one, like that. So think of that when you're thinking of how a function is loaded into the stack. So even if you have main, there is a function that called main, and there's a function behind that called that function and called that function. So it usually starts with the LD. LD is the dynamic loader. What is this? LD is a dynamic loader, pretty much. It's what is called by the kernel to load a program into memory. So stuff happens, whatever, and then you have this function that is dash dash start. So dash dash start is a libc function that calls the main function. So think of it as like, let me open this actually. Let me just have this to draw. Curly draw. Yeah, actually I had it. All right, I didn't even need to. Anyway, I just want to show something. Let me push it to the side and then have this. So you have okay. So you have a function called dash dash start. By the way, there's usually another function before that calls dash dash start. I don't remember, but you can just check when you try to disassemble any binary and then check the calling, the functions calling each other. Now think of start as like the function that has your constructor and has your destructor. So what I mean by this destructor, what I mean by this, it's pretty much like, so your start has a pointer to where the program begins, so that's your main function, and has a pointer to how to exit that function. So, no, actually, yeah. Sorry, I am confusing myself. Yeah, it's dot slash init and slash fini, actually. And this is usually called before start. I'm sorry if I'm confusing you guys. You can just ask questions. So there's a slash init and slash fini. So init handles like, okay, how are we starting this program? You know, like what do we need to do to begin this program? So init calls start. Starts calls main, actually. Start calls main. Yeah. So now think of it this way. The outside stack here, the outside rectangle, the purple one, is your stack for slash start, right? Imagine that you're within slash start, and then you want to call a function. So the first thing that you do when you're calling a function is you have to put in the return address. It's like, when I want to slash finish, where do I finish and go back to? Like you need a place to return back to. So that's why the return address is usually like the bottommost part of your stack. So you put the return address and then you enter a new stack. So in this case, we're entering main, the green rectangle here. So the thing at the bottom is the RBP. It's pretty much telling me this is the pointer, this is the base of this stack that represents the main function. Now, because that's like the bottommost part, to be able to like protect against like, okay, someone wants to escape this stack by like overwriting the return address, we put a stack canary. So a stack canary is a value that is usually okay, so there are different types of canaries, I guess, but it's just a value that is put before, after the RBP, to be able to protect against overflow, against like return addresses or return address overwriting. Yeah, so there are different types of canaries. There is like random canary, there is canary that are static, those ones that are compiled, that are generated during compilation. Anyway, when you see a stack canary, just know you can't do shit. You can't do anything about overwriting the return address until you know what the canary is, right? Because there's a check there's usually a check. Let me show. I need to set this stuff up visually. Okay. So let me just now I use a redelf to check the symbol table. So because it was not stripped, we can be able to see the symbol tables. What this means is like a symbol table has a mapping of like the names of functions, the names of objects, and their offsets. Yeah. So this is super important, by the way, because before you run, depending on whether the binary is PIE or not, the offset does not change. So you need the symbol table for the program to know where to find stuff, pretty much. So you first want to go through this to look through any custom functions that have been put in the program to help you have a starting point on where to look, right? So we have main here. I guess this one is always expected. We have main. Do we have another thing? Um, okay, we have gets. That's pretty much wanting to get input. Printf. Right there. I think that's it. Yeah. All right. So after that, the next thing I usually like to check is just check the sections. So the sections are these are pretty much usually the same for ELF binaries. They usually have the same sections. And text is where you have your code. So it's always executable. .fini is what I talked about earlier, right? .fini and .init. You have your PLT and PLT because the binary was dynamically linked. You have arrow data. So I like to check this. Arrow data is read-only data, so you can see comments there or some hard-coded strings that we can be able to maybe use. So I do. Okay, nice. So let's just copy this and then check it out. All right, so do we have anything interesting here? Congrats, you passed all the restrictions, have a flag. Okay, we have a slash flag .txt. So we know that probably they're trying to read through a flag. Welcome to CyberCon, it won't hurt, leave a feedback about the server. All right. So this tells me two things. Tells me one, that there are probably two inputs that are required, right? Because there's this welcome and then there's the kathingi here. Alafu there's this and there's a kathingi here. And then there is a flag.txt. So what I'd want to do first is, okay, let me create a dummy flag. Flag. Okay, and I put it in flag.txt. All right. So now we want to disassemble the code and see what we can gain from this, like what we can do. So let's start. You can actually use Jidra, which is, I guess, easy, by the way, because it decompiles the code for you. But for me, I just like using this because Jidra sometimes can distract you when you just look at the compiled code. Yeah. Any questions? All right. Okay. So what can we know about main? Okay, so these three things here, let me just copy this first. Sorry, I'm going slowly with this one because I think for the rest we'll just rush through. Yeah. I just want to like go through the concepts a bit. All right. I hope you can see, right?
Yeah.
Okay, sawa sawa. All right. So these three functions, I mean these three lines, I usually call the. Okay, I forget the name. But they're pretty much like the entry thing. Like think about it as a constructor. Now we are creating our stack. This is what we do, and then down here you have leave and read. So leave compresses the opposite of this. But this is like the distractor. Okay, now we are destroying our stack. We need to like pop RBP, we need to pop our RSP, things like those. Anyway, so the good thing about this, it can, for just by glimpsing at it, you can already know like what is the offset to the return address, right? Based on what we saw here. We know that the return address is just below RBP. Here I can make a wild guess and say that offset to return is at OX what? OXBO. Now this doesn't necessarily mean that this is how we will exploit this binary. It's just good to like have a view of like, you know, how big this thing is, or like if I'm putting my input top there on the start, how much will I need to like get down to the return address? Yeah. Okay, let's continue. Yeah.
Levanto, I have a question.
Uh,
So when you like notice the initialization of the stack is starting with push RBP, does that necessarily mean that it's a 32-bit binary? Or does it, because I don't think like on
uh,
64-bit we have push RBP. I could be wrong though, but I guess
Actually, this is 64.
that's 64-bit. Okay.
Yeah, yeah. So it's usually there's usually wait. RAX, let me just do it here. So there's like a way to know. There's RAX, EAX, EAL, and AX. AX and AH. So this is usually like the biggest. I think it's a Q word. They call it Q word. This is 64. When you see it being RX, this is 64 bit. 64. If it's here X is 32, and then it goes lower like that. This is 16. They call it AL. They just call it AL, I think. And then this is 8. Yeah. So yeah, I think I understand what you're meaning though. You're asking like, so this part up here is usually the same, by the way. Because
Okay.
you have to push, yeah, yeah. But what you're asking, I think, is sometimes in some programs, I guess, you can see that for them to like, they usually push the parameters into the stack, right?
Yeah.
Kuna zingine, they usually like push parameters and then they call the function. And then there's another one, they load parameters into like EDI, ESI, and then they call the function. Uh, I don't know what's up with this, but I guess it's just depending on the calling, what do they call it?
Convention
Calling,
or
exactly, calling
yeah.
convention. Yeah, yeah, yeah. Yeah. But this is 64 once you see it like that.
All
Let's
right.
just confirm sanity. Yeah, here it is. 64 bit.
Sweet.
Okay. So now we already loaded we initialized our stack, right? And then we notice two things here. We notice, okay, they move something from EDI into RBP, and then they move something from RSI into whatever. So this gives me some thinking that there might be like some parameters that are being passed from here to here, right? This gives me a hint. If you see like from the beginning of your program that you have something like this, move something that is in a variable, especially EDI and RSI, into some point in the stack, it can give you a hint that there are parameters that are required. It's not always that they're required, but you just know there's some values that are being moved. I guess in this case, we didn't really need them. But yeah, this is the case. Okay, and then we continue. So here is where we load our canary. into array X, and then we move array X into RBP minus 0.8, right? Remember that this is just above the RBP. So our canary lives now above the RBP. Okay. What do they do here? Not effective address into this, call this into RBP minus 0.98. Put. Okay. So the thing that matters here, by the way, is usually if you see a call, it's always good to work backwards. Don't start this way because there might be some stuff that they're loading from a place in like a data section into some register before they put it as a parameter. So if you see call, it's always good to go upwards like that, not like this. So in this case, it just tells me there is some string that is being put in RDI that is then called inputs, right? And I can be able to get it because here it is, 2058. I think when we go to our notes, we go to 2058, it's pretty much here, right? So it says, welcome to Echo Server, to CyberCon's Echo Server. Yeah. All right, so we know there's a call to puts, nice. And then, what is this? There's a call to printf, all right? And then, what do they take? They take another string, which was a 27b. 27b. It's pretty much the thing, the kathingi for like putting in your input. So if we check it here and do chal, yeah, it's pretty much that thing there. Okay. All right, what's the next part? It does a printf, we're done, and then it reads input, right? So here, let's see. So what is it reading? It's reading from 0. Okay. I usually like to just open this for safety. I just check the parameters that are expected from read. Okay, we know they take a file descriptor, they take a buffer, a place to put in our input, and then they take a count. Nice. So the calling convention here is usually you load your parameters oppositely. So like the one that is at the bottom here is the first parameter pretty much. So we're reading from standard in, which is usually file descriptor 0. And then we are reading it into, what is array X? We are reading it into RBP minus 90, right? RBP minus 90, and then we are reading 16. X16, nice. All right, then let's continue. The next important thing here, I guess, was the printf. Because what is printf doing? Printf is taking our input and then pretty much printing it out. Now, here's where the vulnerability is. If you call printf without giving it a format like that, it takes the input as the format pretty much. So like FC. Anyway, let's look what this has. Yeah, so format is a string that contains the text to be written out to std out. It can optionally contain embedded format tags and can be replaced by the values. Yeah. So if you give it some format specifiers, it modifies the input to give you, as per the format. So that's why if you put in, let's say if they have an example here. Yeah, if you have a %d, what it does pretty much is it converts the input that you gave it into an integer. There is let me see. There is a link I sent that I shared somewhere here about how printf works. It just gives you like some lower level view to understand how this stuff works. So where is it? Using printf with formats linking, blah blah blah, loading. mapping. Is it this one? Oh yeah, pretty much. So it gives you an example of like if you have %d, what happens pretty much. There's usually a check to check which type of specifier is given after this percentage. If it's a %d, it does I to a what? So it converts the input into an integer and then gives you back that. So pretty much it's like, okay, I've given you something, just format the string that I've given you to match this format specifiers. But then there are like some format specifiers that you can use to leak addresses or to put stuff into an address. And that's usually %n and %n you can use to put stuff into an address. %x, %b you can use to leak stuff. There's another link I think I have somewhere. Let me share this stuff on the chat. Just a minute. There's that. Let me see another one. I think I put it here. Oh yeah, format string vulnerabilities. This is a really nice like paper. It's like 30 pages long, but it's really nice. It shows you like the different types of format string attacks. It really explains them well. Yeah, I think it's good to look at it at your own time. Anyway, let me also share this here. Yeah, okay. Now let us continue. Where were we? Yeah. So now we know that, okay, we can be able to use this printf thingy to manipulate what we want to get back, right? Okay, let's just give it a try. We say %p, 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 %p. What do we get? Nice. We see what was just at the stack, right? In front, I mean, on top of the stack. But now we need to know like where exactly are the stuff that we want to leak. Where are they, right? Now we know we want to leak a bunch of things. First thing we want to leak is the canary, of course, right? We need to leak the canary so that we can know, so that we can be able to bypass it and go to the return address, right? Another thing we noticed that this binary is PIE enabled. So what that means is that every time we run the function, we won't be able to know like we won't be able to know where the program was loaded at, right? So we need to know where it was loaded at. This is why we want to leak a return address. Yeah. Now remember, where were we? Remember we have something that looks like this. We have something that looks like this. Our input is maybe somewhere up here, right? Somewhere up here. So we need to see how much it will take us to get to the stack canary down here. And after that, we add 2 and get the return address. Pretty much it. Okay. Now, I'm also not so good at this stuff, but let's see if I can be able to figure out a sort of trick in terms of getting the offset without having to do Jeff. So let's first just break at main. Let's run. Let's disassemble our main function. And then let's break somewhere. Let's break before we print our input. No, here, down here. Let's break before we print our input. And let's break after we print our input so that we see something. Okay, so we continue. So let's give it %p, 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 right? This is before we printed our input. Let's examine the stack. If you get lost, just ping me. Like just stop me in the middle, please. All right. So what is this? We're inside main, of course. Let me just confirm something. We're inside main. On top of the stack, we're at 4D0, right? But our input was put at RBP minus 90. So it's not on top of the stack, but it's like somewhere in the middle. It doesn't matter though, because once it gets called by printf, it will be on top of printf. What am I saying? Yeah, printf will pretty much uh, start working on this input from where the input is, right here. So now, let's do this. Let's actually just get the inputs, get the leaked addresses first, and then we work back from there. I'm also a bit slow in this stuff. So if you figure out quickly how to check the stack, please let me know. Rusty, did you do this? Hello? Anyway, okay. So here we are. Nice. Is your audio on, or can you speak? Maybe if you have a quicker way of doing this. For me, I'm usually pretty slow when it comes to this. Sorry, I have to do some small tinkering here just to get a bit of. Just a minute. All right. Sweet. I wanted to explain something fast. All right. 1, 2, 3, 4, 5, 6, 7. Okay. Sorry if I'm a bit disorganized. I'm just going back and forth to kind of explain something before I continue speaking. All right. I just wanted to show you guys how the stack looks like inside printf. Explain some things here. Let me remove this. If you're confused, just ping me. Just hit me up so that I stop. Okay. So this is how our printf looks like. If you remember, the purple box here is dash start, right? And that stack is what calls our main stack, yeah, which is the green one. Now forget about the orange one. This was another thing. Oh my god. Anyway, let me maybe remove this one instead. Let me remove this instead, just so that this makes sense. Just a minute. Let me go up. Let me go up. Alright, this stuff needs to go up. Up. This needs to go. Where is this? Needs to go up. And then this stuff needs to go up. And this one too needs to go up. Okay, and then push this here, I guess. And then this does not need to be here. Okay. I'll just modifying this to look like what we are working on now. So I guess this needs to get out and this needs to be main. Where is it? This needs to be main. Okay. So here we are. So the purple stack is for the / start. It calls our main function, which loads the RBP stack canary, and then gets our input, puts it somewhere on the stack. In this case, it's not on top of the stack, right? Doesn't matter though, we'll see. And then calls printf. Now, if you get to read that article that I sent around understanding printf low level, you will get to understand why when we spit out like the first five pointers here, 1, 2, 3, 4, 5, we get this stuff here that doesn't seem to make sense. 1, 2, 3, 4, 5. And then after that, if you can see, we have ZFFF, whatever, 1688. And that was pretty much on top of our stack now. Oh my God. I don't know if I'm making sense at all. I'm not sure if I'm making sense. Guys, am I making sense? Hello?
Okay, personally, I'm kind of lost.
Just ask me, guys. You know, like I don't want to keep talking and like maybe I'm the only one like vibing here.
Uh, Go back to like where you said the address was what on the stack or yeah, something like that.
What do you mean? Or
No, like
okay,
when you're
let me
talking
just
about the like where you're using printf to leak addresses on the stack, you talked of the very last
oh
address and yeah,
okay.
just that part, yeah.
Okay. So let me redo this Kwanzaa. Let me just put it until we are past 5. We are like at 8. Let me just, this is 5. Let me copy this and then let me just copy this. Hey, are you okay?
Like,
Oh?
I'm also lost.
We cannot hear you. Okay. This is 1, 2, 3, 4, 5, 6, 7, 8. I understand why it's bringing these issues. By the way, I know there's a very easy way to do this in like pwntools, but I don't use that a lot, so I'm sorry. Anyway, okay, so now we put in 8, right? 8%. I just dropped out for some reason. Sorry. Okay, so now we put 8% P's, and you're like, look for me 8 addresses that are on the stack, right? Okay, let's continue and see something. So let's just take this. This is what was leaked, right? Let's take it and maybe put it in another place here, just so that we can analyze it a bit. So these are the addresses that were leaked, right? And then let's examine the stack. Now this is after, oh no, this is before we've leaked printf actually, right? Is this before? No, this is after we've leaked printf, I think. Yeah, and let's take this. So this is how the stack looks like after we've called printf and after we've leaked this stuff, right? Now, we just want to get a bearing of what exactly was leaked, right? Now, we can check this one. This is OX101 whatever. And we can find it here on the stack, right? It's like the second address on the stack. So the first and the second address of our main stack is not the first in this case, right? Because we remember we were inside printf when we did the format string attack, right? So these first things here, these first 5 things here are from where? They're from the printf. So this is why like I drew this stack like this, just to have like some visualization. That it has like a distractor and then does something. It's just some low level stuff you can check and see. Anyway, I hope that's a bit clear-ish now. Is it?
Yeah, totally.
Okay, nice. So Sasa, when we're here, I think now we can try to like get the offsets, right? Now we know that the first 5 addresses, these first 5 addresses are from where? Are from printf stack. Okay, sweet. Then we know, okay, we didn't load our input at the top of the stack. So we know that, but this doesn't matter anyway. Once we get out the printf stack, we know that now we're on top of our stack, right? Which was how much? Which was OXB0 offset from the top of the stack to our return address, right? Okay. So that means that if we want to calculate the stack, the how many addresses we need to leak to get to the return address, it will be OXB0 plus OX what? OX, oh my god. OX 1, 2, 3, 4, 5. 5. I hope I'm right. Plus 5. So this will give us OXB 5. No. Sorry. I'm so sorry. It's not 5. It will be OX8 times 5, right? Because we're pretty much, this is like the size. The size is not, oh my god. I feel so bad. I'm confusing myself and even confusing you guys. 32. This gives us B plus 3 CDE. OXE2. OXE2. Okay, so what I'm doing here is pretty much trying to calculate how much it will take for me to get to what I want to print out, right? So in this case, you can just count it along anyway. You can just do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, blah, 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 and get all the way to where you want to get. Or you can do it this way. You can just calculate it and divide this stuff by 8 and just get how much you need to get to where you want to get. Let me just get something here, just a minute. I'm trying to see this just for sanity's sake that I have the correct offset. Input from
Are you looking at
27. Okay.
where you look at the offset? Because if you look at the one like the is it $9 percentage periods percentage, that one, remember that one changed because of the
Yeah,
yeah
I was looking at this one,
okay.
canary from input. Yeah. To just make sure that my calculations here are correct, which I think they are. So OXE2 is what? Hexadecimal E2. This gives me 226. 226 divided by 8. This gives me 28.5. Cool story. Based on this diagram that I drew here. I guess I already shown the answer. Okay, so based on this diagram here, pretty much what we leaked here was main's return into libc ret, right? This is not, this will not become like this address is not within main. This address is in the dash dash start, this one. So this is why, by the way, I think we had a problem when we were doing this stuff during the CTF. Instead, we could have used an address that I think is pretty much here. Before we call our printf, we of course have to remember what we said. Before you call a function, you leave a return address behind so that when you close, when you destruct, you end up back to where you were, right? In this case, as you can see here, we're on top of our stack, right? We passed our input and then we called printf. But before we called printf, we have to leave back a return address, which is up here. So which is what? Which is 1, 2, 3, 4, 5, which was the printf stack, then plus 6, 7, 8, 9. So that's why you do, what is this? %9p, %27 slash p. And then that will give us, where is it? Yeah, that will pretty much return to us now the canary, right? And it will return to us a point in main where we come back to, right? After we do the printf. That makes sense, right? Okay. Yeah. So let's just create something here. Edit by imports. Okay, and then we do IO is equals to process. And then we have IO dot receive until this, and then we do IO dot send line. We send %. Actually, I don't need the format since I already know it. I send 9 this, and then I send 27 this, and then I receive. So I do results is equals to io.ref. So I do a decode because it will be in bytes, and then I do results dot split. I split it by the full stop, I guess. What that means is that my return address will be at the first split, and then my canary will be at the second split. Canary will be at the second split. Okay, now I convert them to hex integers. Correct, 16. And then I say canary hex is equals to P64 canary. Actually, I can just do canary is equals to P64 canary. And my return address is equals to P64 return address. Okay, nice. Now we can just do this to just for sanity. Let's print canary. Canary. And then let's print return address. address, return address. Okay, nice. So this, when we run it, Python a.py. Okay, what is happening here? Invalid literal for blah blah blah. What did we get back? This is weird. Let's print our result and see. It's probably because we have to do two rec, I think. Nothing. Recv result plus is equals to io.recv. The code. I think this will also fail because I'm trying to do this shit here. So now I do results is equals to results dot decode. I better work. It better work. Okay, it did work. Even though I'm getting an issue here. It wouldn't invalid literal for this. It wouldn't have to leave the... What the hell is this? What's up with the record?
I think the issue is
It should go receive
for
value.
for the canary, you are actually not just getting the address, you're getting the address plus the string that says it wouldn't hurt to leave
The other
South Africa. Yeah. So
yeah, I figure
the uh-huh.
uh, sorry, I should just put receive line, right?
Yeah,
So that I do away with this stuff here.
yeah, for
Let me
sure.
just try with the first one, I think. Results is equal to result of the code. Yeah, you're right. That was my problem. Thank you. Okay,
You're
let me
welcome.
just put it back
And
here.
if you're interested, I'll show you like an easier way to do it, especially like if you get yourself in the situation where maybe the binary is like you run the binary and like you're already given an address and you need to grab that address from the line. You could just use regex to
Ah,
grab the address. Yeah. So
okay, nice,
yeah,
nice. You can show us after this. Let me
yeah, for
just
sure.
finish this.
Cool.
Yeah, all right. Sour. Okay, so now we were able to leak the addresses that we want, which is nice. Now let's go back to other stuff. All right, so let's go back to disassemble this stuff and see what's up. Um, I think we had it here. Main. Yeah, we had our main here. So we exploited this, and then now they're telling us what? They're telling us here with the printf, I think this is where they say you can leave feedback to the server, right? And then they put it in RBP minus 70. The input that we, right? They ask us for an input and put it at RBP minus 70. That's something to note here. All right. And then after that, they just do a stop check and we leave. Okay, nice. So let's just figure out first the offset from the second input to the return address because I think that's what we want to do. We'll figure out what we're jumping to after, but let's first figure out the offset from the input to return. Right. So in this case, we have OBP minus 7. This is just simple math, I guess. Actually, it's pretty much OX70, right? It's pretty much OX70 to get to return. Yeah. All right. So now we need to create our payload. Another thing we need to remember here, sorry. Let's see. There was a function called call me maybe that we need to look at. Okay. What does call me maybe do? Okay, call me maybe. It takes no input. It looks like it takes input, but I think we don't need to concern ourselves with that. And then it's std out something here. It does an fwrite. Takes in, let's see what the string says. 2008. 2008, it says congrats, nice. And then 203F, 203F, have a flag. Okay, and then it opens something, which in this case, I guess it opens a file. And then it reads the file, and then it prints it out for us. 24A flag.txt. Okay, nice. So pretty much we know now that we need to jump to call me maybe. So what we need to take is this. Let's take the offset to call me maybe. Let me clean this up. So now create payload. So call me maybe maybe is equals to, what was it? OX something, OX1FC. All right, and then we have our offset to return. All right, there's something we forgot to do. We got our return address, which is nice, but we need to get the base. So the base address here is what? Base address is pretty much our return address. Return address. I shouldn't have put it under P64 first, actually, because I need to do some calculation here. It's pretty much our return address minus, what was it? Where we come back, right? Where we come back from printf, which was something 5. Was it this? It was 5, right? 1355. If I can remember, we can just check here. The reverse cut a.py base address plus ret. What is this? Main address. Oh, BC. Oh my god. Okay, sorry. I need to do this again. Break, main, run. I need to break again. Disassembly main. I need to break after the printf. Where is it? After this printf. Okay, break here. Right, continue. I do %9/p, and I do %27/ p. And then, did we load it already? Yeah, we got it. Here it is. Oh, yeah. Which is actually this 12CB. All right. So now, if we go to here, pretty much main. Okay. So it will be minus OX 12BC. 12BC. So that's our base address. So so to get call me maybe address, it will be base address plus at P64, of course. Okay, nice. So now we need to create a payload, which becomes payload is equals to our junk A plus. We don't jump all the way to the return address. We need to remember that we have to put in our canary. Yeah. So pretty much OX70 minus 10, right? Because the difference between the return address and the canary is 2. We have the RBP that sits in the middle. So this will be plus OX60. And then we have to add our canary. And then we have to add OX8. We have to add, I will explain a bit, but just a minute. And then we add maybe. Okay, I think that's pretty much it. And then we do io dot retrieval until this. And then we do io dot send send line, sure. Payload, and then we do io.rec line. We do response is equals to that. And we just do print. Alright. Expecting some errors here. Alright. Can only concatenate string to string, not byte. What am I doing? It should be B. B, B. My canary is good, call me maybe is good. Yeah, I think that should be. Smash stacking detected. I think I have a problem with my offset. Alright. 60. I need to confirm something. 104. What is 104? Decimal 2 hex. 8. Oh my. Yeah, I think that was my problem. Yeah. So if I have 70 and I minus 2, I don't go back to 10. I have 70. This gets me to the beginning of the to the beginning of the return address. Oh no no no! It gets me to the beginning of RBP actually. Yeah, makes sense. Okay, so in this case, I do 70 minus 8, I get 68, and then I add my RBP. So this gives me 70, we're at the bottom at RBP, and then I add call me maybe. Okay, makes sense. All right, and that is it. We have the flag. If we add another receive line here, we'll be able to see the flag. That is it. Okay, so that was what? That was Baby Rob. I'm sorry I took some time and that was a bit confusing. Any questions before John Collins shows us the the stuff that he wanted to show us? Anyone with a question? Okay. Muginjutsu, you can show us.
Awesome.
Let me stop sharing my screen. Yeah.
Give me a sec. Okay. So, okay, let me just start another script. So we had, so from phone, and then we want to, so this is how I initialize or basically just start, or how I specify the binary basically. So what's it called? Child. And what we want to run that as a process. So the good thing about doing this is once you do this, it knows, okay, that's the binary. So when you're doing this, you just say process and it knows, okay, I'm using that binary. So what we were like sending what's this? I normally struggle with this. Is it like this?
No, it's the other way.
Oh, it's
%9.
percentage
$.
and then dollar. Oh yeah. Okay, cool. So wait, were we doing this or just with the P only, like to link the first two addresses? I'm confused.
Oh, we did %9 $P to link the ninth address on the
Cause
stack. Yeah.
cause they were two though, but okay,
Uh-huh.
cool. There were two
Yeah,
of
yeah, yeah. So
them.
that was to link the return, and then the other one, percent. I did a dot %27.
27. Ah, there we go.
Yeah.
So you want to send line this, and let's receive and see what we get. So we get now the addresses, right? So the first one is what was the first one again? Because this is a canary. This is is it the pointer to ret that calls like ret inside the libc start, I guess, or
So that's actually the main
oh
the
the main.
main
Okay,
yeah.
all right. So basically, so what I do at this point is I import re for regex, and how I do this it is I'd say addresses is re dot find all, and then I have 0x and then this to say like okay, so it starts with 0x, and then in here we'd have a lowercase ASCII and a number. So like we have 55, so those are digits. Then we have BA, those are, that's ASCII in lowercase, and then a digit, then ASCII, and so on and so on. So I'd have like A to Z 0 through 9, and I put a plus. So what that will do is it will grab everything that starts with 0x and has, that inside there. Not really inside, but just next to it. And it will do that for like, for everything within, what you receive. So that's why I'll come here and say r.receive. So if we print addresses, um, so we need to maybe, okay, we could do like IO. I do, okay, that's fine. Yeah. Cannot use a string pattern on a byte object.
Or maybe you do dot
Because,
decode.
yeah, exactly. Let's see if that works. Yep. So now
Oh,
you'd
that's
come and
cool.
say that, um, this and this address is, addresses the first thing, and the other address is, something else. And now you could like print them. Yeah. So that's how I usually do it.
Nice.
And
That's
it's
really
really
cool.
cool because it really helps you grab them very fast, especially like if you have a long string and then the addresses start from there. So yeah.
Mm. Nice.
Yes. Yeah, awesome.
Thank you. Okay. Now we go to the next one. Just a minute. Okay. Is this thing not charging? I'm trying to charge my laptop, but it's not charging.
Oh no.
Uh, Oh, that's a bummer. We have approximately 20 minutes, I guess. This change of mine is very old. Anyway. Okay. Let's continue to the next one. The next one was which one? PT root or something? Ah, there was Hunter, right? Hunter. Okay.
The Hunter and then the PTR Zor.
All right.
Yeah.
Let me just make sure I have. All right. Actually, there is something about Hunter. So